Well, once again, we meet for me to stretch your brains and for you to stretch mine a bit too. We're going to be talking today about some of the properties of the real numbers with which you are very familiar. But these are properties that, excuse me, don't have to be assumed. Many of these are properties that can be proven. And so we're going to show you how to do that. And we're also going to talk about some stuff with which you are probably not familiar. And we're going to start off with that. So let's pray, and off we go. Father, thank you again for opportunities to stretch our minds. Lord, we know that the animals don't really have opportunities to stretch their thinking very much. And Lord, we thank you that we are more than just food and clothing and simplicity. That we can think abstractly. And Father, I pray that you'll help us to think abstractly this afternoon and to understand the things that are coming at us. In Jesus' name, amen. Okay. We talked about what a field is. We've talked about what a ring is. Every field, of course, is a ring. Most rings are not fields. A field is a non-empty set where you can add, subtract, multiply, and divide by anything other than zero. And the multiplication is commutative. A times B equals B times A. The fields that we know the best are the field of real numbers, which they taught us about in junior high school, in fact, in grade school. The field of complex numbers, which is the field that you get when you attach the so-called imaginary number I to the real numbers. The field of rational numbers. And there are many, many other fields that have properties that are a little different. For example, as soon as you have a field that is infinite, then it really carries a copy of the rational numbers inside of it. Because if it's infinite, it has to have a 1. If it has a 1, it has a 1 plus 1. And it has a minus 1 and a minus 1 minus 1. It has negative 2 and 2. And it has a 3 and a negative 3 and a 4. So it would have to contain all of the integers. And the smallest field that contains all of the integers is the set of rational numbers, because those are just quotients of the integers, other than having 0 in the denominator. So any infinite field contains some kind of a copy of the integers. Now, what do I mean by some kind of a copy? In algebra, there is a type of function called an isomorphism. We've actually dealt with those in this class, but we didn't talk about them by that name. An isomorphism is a function that is one-to-one and onto, but furthermore preserves the addition, the multiplication, the subtraction. It preserves those things within the ring. So if I have an isomorphism from this first ring, say R sub 1, into and onto the second ring, R sub 2, and if F is my one-to-one onto isomorphism that preserves addition, here's what I mean by that. That F of A plus B is equal to F of A plus F of B. Now keep in mind that the plus over here is the plus in R1, the plus over here is the plus in R2, and those don't necessarily have to have any similarities whatsoever. The plus over here in R2 might actually be what we call multiplication in some other ring. And I don't want to get too strangely into that. You will cover things like that in linear algebra if you take linear algebra. But the punchline is that there are lots of different kinds of rings, lots of different kinds of fields, and lots of different kinds of addition, multiplication, etc. A little while ago, I made the comment that if a field is infinite, that it contains, and now I can use the word, an isomorphic copy of the rational numbers, meaning that there is an isomorphism from that between that ring and the rational numbers. It's 1 to 1 and on to, preserves the addition, the multiplication, and etc. That being the case, the way that an algebraist thinks is that if two sets are isomorphic, then I don't have to study both of them. I can just study one of them, and I get the properties of both. But that statement intimated that maybe there are fields, for example, that are not infinite. Are there finite fields? And the answer is, of course, why would I have asked you if it were not so? There are finite fields, and let me address you back to the clock. We've talked a little bit about this. On the clock, the dial, if you're old enough to remember analog clocks, where the little second hand goes, right? You see 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, and we've talked about the fact that the 12 is really the same as 0, because if I start a task at 7 o'clock in the morning, so it's 7:00, and I work on that task for 9 hours, then I'm done with that task at 4 p.m. So in some sense, 7 plus 9 equals 4. Now, how does that happen? And the way that happens is because every time I pass the 12, that counts as a 0. So every multiple of 12 is equivalent to 0. Excuse me. Now suppose, we may have talked about this before, suppose that that's my entire arithmetic. My entire arithmetic is made up of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. There's no 12 because 12 again is 0. And those are the only numbers. Then my new addition is 7 plus 5 equals 0. So what do I mean by -7? Well, there's no negative on the clock, but the negative of a number is whatever I add to that number in order to result in 0. So -7 is really 5. -4 is really 8. And 4 times 5 is really 8. Because we would think of 4 times 5 as 20 normally, but if 12 is 0, then 20 is 8. Technically, the answer to an arithmetic problem in this particular setup, and it is a ring, by the way, 0 through 11 does form a ring because all those properties of addition and subtraction and multiplication are valid. It is indeed a commutative ring because on the clock, 3 times 4 is the same as 4 times 3. 3 times 4 and 4 times 3 are both 0. So the way that the arithmetic pans out is that the answer to any arithmetic problem comes out the remainder upon dividing that answer by 12. The set 0 through 11 with the properties that I've just been describing is a ring, a commutative ring with 1 that is finite. It has 12 elements in it. It also has what are called zero divisors. Now, what do I mean by a zero divisor? A number is a zero divisor if whenever I multiply it by some other number, I can get 0. So for example, 4 and 3 are both 0 divisors because 4 times 3 is 0. 6 is a 0 divisor in this new ring because 6 times 2 is equal to 0. 2 is also a 0 divisor. 0 is always a 0 divisor because 0 times everything is 0. And so this set, which I call Z mod 12, the integers mod 12 are 0, 1, 2, 11, where all multiples of 12 are 0. Okay, now there's some stuff going on in the background here, and I don't want to stress it too heavily because we're not going to be really studying finite rings and finite fields very much, but you will be studying them a little bit. You'll have a couple of homework problems on them. But what's really going on in the background is the equivalence of integers. We're going to define an equivalence relation on the set of integers by n is equivalent to m if and only if n minus m is equal to 12 times something. Okay, if the difference of two numbers is divisible by 12, then the two numbers are equivalent. So for example, think about the face of the clock, 15 and 3 are equivalent because 15 minus 3 is divisible by 12. In fact, it is 12. 27 and 3 are equivalent because 27 minus 3 is divisible by 12. And Z mod 12 has these several 0 divisors. Now, a special thing happens. Let's pretend that we live on a planet where there are not 12 hours in the morning and 12 hours in the afternoon, 24 hours in a day. As a matter of fact, it's not actually true that there are 24 hours in a day. Not even here. There are 23 hours, 56 minutes, and 4.095 seconds in a day. Unless you think the error of that there are 365 days in a year, that's not true either. There are 365 days, 5 hours, 48 minutes, and 45.51 seconds. And that may be changing. It was that when I was a kid, but who knows? It's been a while. But if you were on a planet where instead of 24 hours in a day, there were, say, 14 hours in a day. There were 7 hours in the morning, 7 hours in the afternoon / evening. Then your clock, instead of reading from 1 to 12, or the way that I prefer to think about it, from 0 to 12, from 0 to 11, instead of reading that way, it would read 0, 1, 2, 3, 4, 5, 6, because every multiple of 7 would be 0 again. That would be the set of integers mod 7. So what's the equivalence there? N is equivalent to m if and only if the difference is 7 times something. So let's consider Z mod 7, which is 0, 1, 2, 3, 4, 5, 6, where multiples of 7 are 0. Now, what happens when we start to stretch each other's minds mathematically? What do you mean by thinking outside the box mathematically? Is there anything about a 24-hour day that is magic? I mean, yes, the day has 24. It just happens to be the way it is on this planet. But there are other planets. There are other places. There might be a place where the clock would have 0, 1, 2, 3, 4, 5, 6 on it, and then 7 and all the multiples of 7 would be 0. There's nothing wrong with a set that's 0 through 6. And addition and subtraction and multiplication are defined in the obvious way. If I'm in Z mod 7, where every multiple of 7 is 0, then what's 2 times 5? Well, 2 times 5 is 3. Because we would think of 2 times 5 as 10, but 7 is 0, so 10 is 3. What is 4 plus 6? 4 plus 6 is 3. What is 5 squared? 5 squared is 4. Because 5 times 5 is 25, but if every multiple of 7 is 0, then 21 is 0, so 25 is 4. And we just get to where we're thinking about these things in a different way. Now, if I can give you some advice on raising children, when you take a trip with your children, assuming that someday you're going to be allowed to be within 6 feet of your children. You could probably do that now. But you're taking a trip with your children, take my advice. It becomes very difficult sometimes to entertain your children. I would recommend learning these concepts really well, because these mathematical concepts of doing arithmetic mod 7, doing arithmetic mod 12, doing arithmetic mod 3 or mod 13, that's really entertaining to kids. Now, lest you think that, I couldn't possibly have a child that would be entertained by saying that 4 times 5 is equal to 6. I would just that would just drive me nuts. But our kids are sometimes smarter than we are. Mine are. So they entertained very easily with little mathematical things, and I want you to get to where this is the idea of abstract mathematics, to think about things and structures that are different. There's nothing wrong with being different. There's nothing wrong with addition looking different in some sets than it does in other sets. So finite fields, finite rings, they do exist. But let me ask you this. When does the ring Z mod n, because I can do this for any integer. I can have Z mod 123. I can have Z mod 14. All of those are rings. Many of them, I won't say most of them, many of them have 0 divisors other than 0. In Z mod 14, 7 times 2 is 0. When do I get a finite ring that is a field that doesn't have any 0 divisors? In fact, where we can divide. Well, let's go back and take a look at Z mod 7. in Z mod 7, how would I define 1 over 3? There's no 1/3. Z mod 7 only has 0, 1, 2, 3, 4, 5, and 6. So how would I define 1 over 3, the multiplicative inverse of 3? Well, there would have to be some number that when I multiply it by 3, it gives me 1. That's the definition of a multiplicative inverse. Some number that when you multiply it by the original number, the answer comes out 1. Well, what do you think might be the multiplicative inverse of 3? What's 3 times 5? 3 times 5, mod 7, is 1. Wow, 3 has an inverse. And of course, 5 has an inverse, it's 3. What would be the inverse of 4? Well, what's a number that I can multiply by 4 and get 1 as a result? Well, let's see. 2. 4 times 2 is 1. What's a multiplicative inverse of 6? And the answer is it is its own. Now, you know that in the set of rational numbers, the multiplicative inverse of -1 is itself, right? -1 times -1 is 1, so they're inverses of each other. Well, in Z mod 7, what is the equivalent of -1? It's 1 less than 0, which is 6. And so it shouldn't be a surprise that -1 times -1 is equal to 1. 6 times 6 is 36, which mod 7 is 1. So a lot of these things are consistent. Every non-zero element of Z mod 7 has an inverse. But that's not true in Z mod 12. What could I multiply by 4 in Z mod 12 to give me 1? Well, let's try them all. Certainly 0 is not going to work. 4 times 1 is 4, so that's not 1. 4 times 2 is 8. In Z mod 12, that's not 1. 4 times 3 is 0. 4 times 4 is 4. 4 times 5 is 8. 4 times 6 is 0. 4 times 7, 28. That's the same as 4. We try them all. 4 times 11 is 44, which is the same as 8. So none of them are going to give me 1. So the punchline to that is 4 does not have a multiplicative inverse in Z mod 12, but it does have a multiplicative inverse in Z mod 7. What's the difference between Z mod 12 and Z mod 7 that would cause me to be able to find inverses in Z mod 7? And the answer is, hopefully somebody said the 7 is a prime. If I have Z mod a prime, that is always a field, a finite field. So no matter what the prime is, the prime could be a very large prime, but still Z mod that prime is a field. Every non-zero element has a multiplicative inverse. So those are some of the things that are fascinating to me, that the properties that we talk about with the real numbers, many of those properties are held by other sets other than the real numbers, the rational numbers, the complex numbers, the integers, the things that we're familiar with. And so consider your minds suitably stretched. Okay? And we've talked about some of these things before. But now I want to start proving some familiar things about the real numbers, things that we've been familiar with all of our lives, but in fact, probably in the womb you were thinking about some of these properties, but that have to be proven. So let's prove some. For example, suppose that I'm in the field R. So for the next several results, our set is the set of real numbers. Okay? Putting the caps on these pens is getting more and more challenging. I don't know if it's because they're tighter or because I'm older. But anyway, this I think in the book is 5.3i. If A, B, and C are real numbers, and A equals B, then A plus C equals B plus C. Now you're probably thinking, duh, of course, if I add the same thing to both sides of an equation, I get the same thing. But this is something that, you know, some of these mathematical systems could be very strange. In the real numbers, this is always the case. Now it turns out that this is always the case in any ring, but let's prove this. And by the way, the same thing works for multiplication. A times C equals B times C, if A equals B. So the proof is easy. We're going to define a function. So for number one, define a function. We'll call it f via the recipe f of x equals x plus c. Now, it should be clear that that is indeed a function. What does it mean to be a function? Well, it means it passes the vertical line test. Does y equals x plus c pass the vertical line test? And the people all said, yes. So this is indeed a function. That means if I plug in two representations of the same input, I'm going to get the same output. This passes the vertical line test, hence, it is indeed a function. So, if A equals B, f of A equals f of B. This is the definition of the vertical line test. If I give a single input, I can't get two different outputs. But if f of A equals f of B, well, what's f of A? It's A plus C. Therefore, A plus C equals B plus C, which is exactly what we had to prove for part one. Part two. I'll bet you know exactly how I'm going to do this. Define a function. Let's call it g. Via the recipe g of x equals x times c. Okay. Now, is that a function? Does y equal cx pass the vertical line test? Well, c would be the slope. Now, if c is equal to 0, then this is the 0 function. If c is not 0, then this thing has either positive slope or negative slope, but either way, it passes the vertical line test. So g is a function. G is indeed a function. So if A equals B, G of A equals G of B. But what's G of A? G of A is A times C. So therefore, AC, what's G of B? B times C. So AC equals BC, and I get to draw my little rectangle. Okay, so most of these things are fairly easy to prove. Many of them just require a sneaky little trick. And so let me get you used to some of those sneaky little tricks. Well, this one has a little trick. This is theorem 5.4. And it goes like this. Let T be any ring, which of course includes the real numbers. Okay? Then this particular theorem could be categorized under if it walks like a duck and it talks like a duck, it's a duck. Let's say the theta acts like 0. If theta satisfies theta plus A equals A for some A, any A, then theta equals 0. We're going to prove that. It's easy to prove. But notice what it says. 0 has the property that 0 plus A equals A for every A. And here we're just saying if theta acts like 0 for just one A, then it's equal to 0 all the time. So it's a little more powerful than it smells. Let's see how we would prove this. Now, one of my favorite modes of proof, if I want to show that two things are equal, I just love to start with one of the things on the left-hand side, equals, 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 equal, and get the other thing on the other side. But sometimes it takes a little bit of a sneaky trick. So, let's start with theta. Theta equals. Now, theta is certainly theta plus the 0 element, because 0 plus anything is the anything. So I know that 0 operates like that on all elements. Theta, all I know is it operates like that on one element. So I've got to stick A in here somehow. Well, this is theta plus. Now, is there another way that we can write 0? How about, that involves A, by the way. Well, how about A plus negative A? This is 0 for our element A. But addition is associative. So this is equal to theta plus A and oh yeah plus negative A. But what's theta plus A? It's A. And oh yeah, negative A. But what's A plus negative A? Same thing it was here. It was 0. So this is equal to 0. So what do we have? Theta equals 0. That is the end of that. So sometimes a little trick will get us where we want to go. Theorem 5.5. In any ring, now I told you before that our set for the next several results was going to be the set of real numbers, and it is. These are all properties of the real numbers, but I don't need the power of the real numbers to get many of these. I just need that it's a ring. And so in any ring T, 0 times A equals 0. Now, we all know that to be true. But if you think about it, why would that be obvious? If I have an element with the property that whenever I add it to something else, I get the something else as the result, namely this element, 0, why would that same element times anything equal that element? Why? What's so magic about if I add it to something, I get the something. If I multiply by anything, I get 0? Why? What's the connection? The connection is this theorem. And this, by the way, is true for every element in the ring. Now, proof. By 5.4, if I want to show that this element is 0, by 5.4, it's enough to say that this element acts like 0 on one element. Because that's what 5.4 said. It said if theta acts like 0 on just one element, then theta is actually 0, no matter what the element was. So if this thing acts like 0 on one element, then it is 0. So by theorem 5.4, if 0 times A acts like 0, with a single element of T, then it is 0. Well, what element am I going to pick? I'm going to pick itself. But 0 times A plus 0 times A is equal to, well, let's see. I can factor this. Which way did I decide to do it? This is equal to 0 plus 0 times A. But what's 0 plus 0? 0 added to anything is the anything, so 0 added to 0 is 0, so this is 0 times A. But notice what I've done. 0 times A plus 0 times A equals 0 times A, which means that this element, 0 times A, acts as 0 on a single element. So 0 times A is 0. And that's the end of the proof. A lot of these are really simple. You just have to think about them a little while before it falls in your lap. Okay. Theorem 5.6. That seems like a logical place to go next. Additive inverses are unique. Now, what do I mean by that? I mean, if A plus B equals 0, then B equals negative A. There's only one thing that I can add to A and get 0, and that thing is this thing, negative A. Now, if you're thinking ahead, you probably already know what I want to do. I want to start with one of these things on the far left-hand side, and at the end, get the other thing. So let's start with B. Is it true that B is equal to 0 plus B? Of course it's true. That's the defining property of 0. But how am I going to write 0? Well, I'm going to write 0 as A plus negative A. And oh yeah, I've got B on the end. Okay. Now, addition is commutative. And I know that combining A with B is a thing that's going to create magic here. So I want the A combined with B. So let's recommute. This is A plus B plus negative A. But what's A plus B? Ta-da! It's 0. So this is equal to 0 plus negative A. And finally, 0 plus anything is the anything. So that's negative A. So B equals negative A, which is what I had to show. Let's see. What should follow theorem 5.6? I know what's this one? Something we've known for a long time. The negative of negative A is A. Two negatives give me a positive. Okay? Proof. Now, what did we just prove? We proved that if something acts as an additive inverse, then it is the additive inverse. And so let's see if this element, negative A, we know that negative A acts as an additive inverse to A. Let's see what about negative A. We know that negative A and I can say now is the additive inverse of negative A. So what does that mean? That means that negative A plus negative A equals 0. Okay. Now, which way did I decide to go here? But A plus negative A equals 0. And by 5.6, the additive inverse of negative a is unique, so negative negative a is equal to the additive inverse of negative a. A. Ta-da! Okay. Now, let's do some we've done several properties of equals. Let's do some properties of inequalities. And before I do that, you may have noticed that my pen is maybe not quite as bright as it was before. So I'm going to take a timeout to grab another pen, and I will be back. It'll seem like microseconds. Hopefully that just seemed like microseconds. Okay, the next thing that I want to prove is Theorem 5.10. And it goes like this, and this you've known for a long time too, but if a is less than b, then negative a is greater than negative b. Now, what do I mean by greater than? All we've really defined is less than. So note, C greater than D means D is less than C. So if we've only defined less than, we need to define greater than in terms of less than, and that's how it works. If C is greater than D, then D is less than C. If you're challenged by which direction these go, remember that the arrow always points toward the smaller one. So whatever is your way of learning those, make sure that you know the difference. But 5.10, if A is less than B, then when I multiply by a negative number, it reverses the inequality. Proof. To show that negative A is greater than negative B, everything down to the definition, then I have to show that negative B is less than negative A. So we must show that negative B is less than negative A. Okay? But we're assuming that A is less than B. So A plus some element, the element is going to be minus A minus B, has to be less than B plus the same element. Okay, I'm just adding the same element to both sides. And that was the additive property of less than, which we did several weeks ago. So I know that this is true. Therefore, now, if I reassociate, what is A plus negative A? And since addition is commutative, I can combine the B with the negative B. But A plus negative A is 0. So 0 plus negative B is less than 0 plus negative A. So negative B is less than negative A. As required. Okay, so that one was easy too. The trichotomy law for the real numbers, you've known since you were in the 7th grade. Given A and B real numbers, either A is less than B, B is less than A, or they're the same number, A equals B. Trichotomy because there are three possibilities, and any two real numbers satisfy that law. Okay? Now, let's take the things that we've learned and let's use these properties sort of indiscriminately to solve inequalities. Lots of students have been challenged by solving inequalities, and I'm going to show you why. I didn't used to like solving inequalities, especially the complicated ones. And the reason was because the method that they taught us back in junior high school was complicated. The method that I'm about to teach you, hopefully, is the simplest one you've ever learned. If you do know this, you probably learned it from me, but wherever you learned it, this is, I think, by far the easiest way to solve inequalities. Solve x squared minus, already I'm messing up, minus 5x plus 6 divided by x plus 1 greater than 0. Solve that for x. Now, what did they tell us in junior high school? At least what did they tell me in junior high school? They said, clear the denominator. But if you multiply both sides by x plus 1, then who knows if you're multiplying by a positive or a negative number. So now you divide it into two cases. If x plus 1 is positive, if x plus 1 is negative, and then you solve the whole mess here, but then you get two factors up here, and then you have to worry about that being positive or negative. So you've got three different factors, and you know, how many possibilities are there? Now I've got to worry about 8 possible sign changes. I mean, it was a complicated mess. This method is very easy. Here's the method. To solve inequalities, here's what you do. First of all, get all the stuff on the left and 0 on the right. Okay? 5 easy steps. Well, that's already like that. All the stuff is on the left and 0 is on the right, so we're cool there. Number 2, factor the left-hand side. Okay? Factor everything on the left-hand side all the way to the bones. All right, let's do that. The bottom, of course, I can't factor any further than that, but I can certainly factor the top. Copy, copy, copy. But how do I factor this? Well, what times what gives me x squared? Of course, that's x and x. And then I want two numbers that multiply together and give me 6, add together to give me -5. That would have to be -2 and -3. Okay? Number 3. Draw a number line with all the roots, all the zeros. Okay? Well, here's a number line. Where is this equal to 0? And the answer is, it's at -1. Where is this equal to 0? It's equal to 0 at 2. And this is equal to 0 at 3. And you don't have to draw it to scale. Doesn't matter what the distances are between these, just put them on a number line. Okay? So I've drawn a number line. I put all three of the roots on the line, okay? Now, test 1 point in each interval. Now this is cool. I'm going to test 1 point here, 1 point here, 1 point here, and 1 point here. Any point that I like. Now, why would this work? If I test -17 and you test -2, why would we get the same answer? The answer is, well, let's suppose that at -17, this thing comes out negative, say. Okay, so I plug -17 into my fully factored version here, and it comes out negative. Then, is there any way in the world that if you plug in another number, say -2, that it could shift from being negative to positive? The answer is no. And the reason is calculus. If I plug in -17 and it comes out negative, and you were to plug in -2 and it came out positive, then somewhere between the two, it would have to go through 0, because this function being continuous every place to the left of -1, it satisfies the intermediate value theorem. By the intermediate value theorem, it would pass through all the intermediate values. And if one of them's negative and one of them's positive, 0 is an intermediate value, but it doesn't pass through 0 because all of the zeros are these three. So if the sign is negative for some place to the left, even -2000, then it's negative all the way to the left of this. Okay? So, what is your favorite number of all to plug in? If this number is in one of the intervals, then I would recommend always trying 0. That's easy to plug in. Because if all the x's are 0, and you plug them, by the way, into the fully factored version, not the original version or any of the in-betweens, but after it's fully factored all the way to the bones, then plug in these points in each of the intervals. Well, let's start with 0. Since none of these points is 0, it lies in this interval. If I plug in 0 for x, then the sign is negative, negative, positive. What is negative, negative, positive? Two negatives and a positive comes out positive. So in here, the thing is positive. Now, what's your favorite number to the left of -1? Let's do -2. If I plug in -2, -2 minus 2 is negative. Let's put it over here. Let's put it in the box that we're not using. -2 minus 3 is negative. And -2 plus 1 is also negative. So an odd number of negatives gives me negative. Now, what's your favorite number between 2 and 3? How about 2.5? 2.5 minus 2 is positive, but 2.5 minus 3 is still negative, and 2.5 plus 1 is still negative. So positive, negative, negative, the whole thing comes out. Maybe 2.5. Oh, 2.5 plus 1, is positive. So it comes out negative. Okay. You know, when you get within 18 inches of the board, the brain turns to oatmeal. It's just a principle of mathematics. And then finally, what's your favorite number to the right of 3? How about 100? 100 minus 2 is positive, 100 minus 3 is positive, and 100 plus 1 is positive. Positive, 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 positive. And so I've tested them all and I've got those signs. I'm done with number 4. Number 5, test the endpoints of these intervals. So I want to plug in these 3 numbers and see if I get true or false. If I plug in -1, the denominator turns into a pumpkin and I can't divide by 0, so -1 is out. So -1 is out. If I plug in 2, I get 0 on top. Is 0 greater than 0? 2 is out. And for the same reason, 3 is out. And so now we can write the solution. We wanted the positive stuff. So this stuff is good, and this stuff is good. Everything else is evil. So -1 to 2 union 3 to infinity is the solution. Now, you might say, well, gee, that's just as hard as if this is positive and that's negative, divided into cases and all of that. But this method is just as easy if I had had 5 factors up here and 9 factors down here. There are more points to plug in, but it's no more difficult, a little more tedious, but it's just arithmetic. So this is by far the easiest method I've ever known for solving inequalities. Let me point out another thing that'll save you a whole bunch of time. Suppose when you factor it all the way to the bones, that all of the factors are linear. In other words, they are all first-degree polynomials. First-degree polynomials. X minus 2 is a polynomial of degree 1. This is a polynomial of degree 1. This is a polynomial of degree 1. If that happens, once it's factored all the way to the bones, then the process becomes easier. You can plug in whatever you want, and I recommend, if it's possible, to plug in 0, and at 0 we got positive. Then the rest of it is predetermined. If this is factored all the way down and all of the factors are polynomials of degree 1, then you can alternate the signs. This one's plus, so this one's minus, this one's minus, this one's plus. So as soon as you get one of them, you've got them all. Saves you a lot of arithmetic. I can just hear the cheering and the yelling going on there because you've learned this new method. Oh, thank you, no need to yell. Let's do another one. Solve x over x plus 3 is less than or equal to 4. Let's use this method. All the stuff on the left and 0 on the right. That means the 4's got to come over. So x over x plus 3 minus 4 is less than or equal to 0. Comment. Let me make this comment, because if you do what I'm about to describe, I will hunt you down, I'll find you, and you'll be imprisoned in mathematician's prison. Many people, as in many people, even college people, write this here and say, okay, well that's the same as this. No, it's not. This is not identical to this, which is what that sign means. The punchline is never use an equal sign as a comma. use a comma, use an arrow, use whatever you want to, but don't use an equal sign between any two things that are not identical, okay? So that's so you won't get shot down on any of your assignments. Okay, well, let's solve this. I don't need this to solve it because I know the method. Everything's on the left. Now, in the 5th grade, they taught you what to do if you were adding two fractions. The answer is find a common denominator. So the common denominator here is x plus 3. The x is already over x plus 3, but the 4 is not over anything, so I've got to multiply it by x plus 3 with a minus sign out in front. And copy, copy, less than or equal to 0. So let's do some arithmetic now. X minus 4x is negative 3x minus 12 divided by x plus 3, and that's less than or equal to 0. Out of which I can factor a negative 3 times x plus 4 now. Make sure you're careful about your signs. And that's less than or equal to 0. Question, is this factored all the way to the bones now? Have I factored it as far as is possible? The answer is yes. Now, the next step is to draw a number line. I'm going to put the zeros of every factor. Well, negative 3 is never 0, not in this planet. Unless, of course, you're talking about z mod 3, but we're not. So when is x plus 4 0? It's when x equals negative 4. When is x plus 3 0? It's when x equals negative 3. Now, I can plug in any number to start with. 0 is not one of these numbers, so I'm going to pick 0. If I put in 0, do I get the truth or do I get a lie? So let's plug 0 in here. If I plug in 0, this is 4, that's positive. This is always negative. And down here, 0 plus 3, that's positive, so the whole thing is negative. And since it's factored all the way to the bones and I don't have any polynomials of degree 2 or higher, then I can alternate the signs. And that takes care of that. Now, which are good guys and which are bad guys? I want less than or equal to 0. So this one is the good interval. But now I still have to test the endpoints. If I plug in negative 4, do I get the truth or a lie? Well, negative 3 is negative 3. But negative 4 plus 4 is 0. Divided by negative 1. So this whole thing comes out 0. Is 0 less than or equal to 0? And the answer is yes. So negative 4 is a good guy. I'm going to include that. What about negative 3? If I plug in negative 3, I get negative, I get positive, but I get 0 in the denominator. That's never a good guy. So negative 3 gets left out, and the answer is the interval from negative 4 to negative 3, negative 4 included, negative 3 excluded. Okay? Normally I would say, are there any questions? But I wouldn't be able to hear them if you did have questions. And so what we're going to do is what we always do. Give me a call, give me a text. If you have questions, that's why I gave you that phone number. By the way, while I'm sermonizing a little bit, I've had several people who have contacted me and they said, Dr. Wolf, I'm really worried about my grade because I was counting on the fact that you were going to have 3 exams. The assignments would count as 1 exam. Out of those 4 grades, you were going to drop the lowest one. But now there's only the 1 exam, and everything else is assignments until the final. The final will be a take-home final. Of course, we're not going to drop that one. But now I don't have stuff to drop. What am I going to do? Because now it's all assignments except for that one exam that we've already had. What am I going to do? I was counting on it. Now, I'm going to give you a little bit of a lecture, and then I'm going to give you a little bit of grace. Here's the lecture. It's never, never, never a good idea to blow off the homework. Well, I can blow that off because we're gonna drop it anyway. It's never a good idea to blow it off, because if you know anything about me, you know that the exams depend heavily on the assignments. So if you blow off the assignments, you've blown off the exams too. But for those of you who took me literally, and I'm glad you did, because I like to be taken literally, I wasn't planning on COVID-19, and maybe you did let a bunch of assignments coast because you were counting on exams, and maybe you take exams well. So you decided not to be diligent on the assignments. You can tell from that sentence how I feel about blowing off the assignments. But if that happened and you didn't do as well on the assignments up to today that you've done, here comes the grace. The grace is, I will let you redo any of those assignments. Now, you don't get 2 shots at any of the assignments from now to the end of the semester, but any of the assignments between the beginning of the semester and now, you may do again, and we'll take the second grade. Make sure that you do better the second time than you did the first time, because it will replace your first grade on those assignments no matter what. But that gives you an opportunity to ace those assignments. Many of you have been really diligent. You've been contacting me in the middle of the night and texting me at 1 o'clock in the morning and calling me at 11:30, and we've been having these phone conferences. The people who want an A are getting it. Okay? The people who haven't been calling but still have questions, I don't know what you're doing in college at all. But you are in college, you are in this class. There's no excuse with this policy that I'm just announcing. There's no excuse to get even an A- in this class, because I'm totally available all the time. Your assignments can be redone, the assignments up to today. And so I highly recommend that you decide whether or not you want to get an A, and then act appropriately. So sermonette is over, class is over. Thank you for being so flexible. Thank you for being the kind of people who do continue to go to class. And I'll tell you, anybody that hasn't been listening to these, I don't know what's wrong with them, because I'm doing them on YouTube, which means you can watch this class over and over and over and over until you get it. I'm not going to erase it until the next class. So people can watch the same class 19 times. There's no reason to not get the material. The punchline is, in life, success goes to the people who work the hardest, who want it the most, but they work the hardest at the right things. Attending this class as many times as you need, calling me for questions, and getting the job done. God bless you guys. I love this class. Please finish well, and we'll see you next time.